Thank you very much. I'm truly honored to be here. I want to thank the Sheikh Hamdan and the organizing committee for selecting me. It is indeed a great honor. And I've learned in my few days in Dubai that you are not only very good in building buildings, building foundations, but also you're building science. And I'm very impressed with the extent of your science building and how you're emerging as an international scientific country. So with that, I will give you this history of 2,000 years of hepatitis. In the U.S., we always have to begin our talks with financial disclosures. But people who work at NIH only dream of having financial disclosures. But I do have some other disclosures. First, my guiding scientific principle is that to steal from one is plagiarism, but to steal from many is research. Secondly, nothing I say reflects the position, certainly of the new U.S. government, which instantly gives it great credibility and relevance. And third, my memory is not as sharp as it used to be, and also my memory is not as sharp as it used to be. So with that, I will begin this timeline, and it began with Hippocrates around 425 BC. Hippocrates was the father of medicine, and he gave us terms such as icterus, when he recognized yellowing of the skin in patients with illnesses, and then gave us the term chiros, our predecessor for cirrhosis, and he observed hardening of the liver. Nothing much happened over the next 2,000 years after Hippocrates, except that there were a lot of wars. And in every war, the combatants came down with multiple cases of hepatitis. Most of that was probably hepatitis A, but a lot was also hepatitis B. It was called campaign jaundice or vaccine jaundice or finally hepatitis A and B. But there was no identified agent for any of this. There was no test. And nothing really advanced until the serendipitous finding in the 1960s of a precipitin line in an agar gel plate. This happened at NIH, a reaction between the serum of a multiply transfused hemophiliac patient who had antibody and an Australian Aborigine who had the antigen causing that precipitin line. Now, in the early years, I was privileged to be the first to observe that line, but we didn't know what it meant. And so my first job as a young fellow at NIH was to look for other populations. So we first tested more Australian Aborigines and found that 10% had the Australia antigen. But when I looked at healthy blood donors, it was only 0.1%. But surprisingly, when we looked at patients who had leukemia, it was also 10%. And in other diseases, at very low levels, between 0 and 1%. So the very first paper on the Australia antigen was titled "A New Antigen in Leukemia Serum." No hint that this was a hepatitis agent. We speculated that this might be an antigen on a leukemia virus, which was thought about at that time and has never panned out. But in any event, that was the very first paper in 1965. This is a picture of Dr. Blumberg and myself done about 15 years ago. Dr. Blumberg is now deceased, but he was my first mentor, and as it was mentioned, he went on to win the Nobel Prize for doing the whole hepatitis story. I went on to be able to talk about Dr. Blumberg winning the Nobel Prize. But this picture again was about 15, 20 years ago, but this is what it actually looked like when I was doing these early studies at NIH. And as you can see, except for my dress, nothing else has changed very much over the years. I also show this to show a picture of Hippocrates again, to show you how much he looks like Dr. Blumberg. If Hippocrates wore glasses, they would be almost identical. Now, Dr. Blumberg was a geneticist. So again, at this point, we still didn't know what this Australia antigen was, but he was a geneticist. I was a hematologist. But he said if this is found in patients with leukemia, and he believed it was an inherited polymorphism, let's think about diseases which have an inherited predisposition to leukemia. And that was patients with Down syndrome. So he began to study patients with Down syndrome. By this time, he was in Philadelphia, and I was back in my clinical training. And sure enough, he found very high rates of the Australia antigen in patients with Down syndrome. But cleverly, he looked not just at large institutions where 28% of the patients had Australia antigen, but when he looked at small institutions, only 3%. And when he looked at Down's patients who lived at home with their parents, it was 0%. And when they were newborn, it was 0%. So this was the first clue that this Australia antigen was linked to an infectious agent. And in these large institutions where contamination is very prevalent, that's how it happened. So it was now an infectious disease, but unknown which infectious disease. And then serendipity played another role, and the puzzle began to unravel. So we had the antigen, we had the institutions, we had the patients with leukemia getting it. But then on the bottom here was a technologist who worked in the Blumberg lab, who one day came to work and her skin was yellowing and she was nauseated, and she tested her own serum for the Australia antigen. She'd always been the negative control in the laboratory studies, and on that day she was antigen positive. So then the puzzle came together that this was an infectious disease, and the infection that it was viral hepatitis. At that time, not known that it was hepatitis B, but that came slightly later. In fact, shown here, it was then unraveled that this Australia antigen was the envelope protein, the surface protein of the hepatitis B virus, and that it was this coating of the Dane particle. The whole virion is shown on the left, and you see the encircling capsule or surface protein, which is the Australia antigen. But very importantly, these Dane particles, the real virus, were in the minority of the observed particles in EM. The majority was shown on the right. Let's see if I can do this. This doesn't seem to work. But anyway, you see those circles and tubular forms in the upper right-hand corner. This was just surface antigen, unattached to a whole viral particle. And there were thousands of these particles for every real virus. And it was because there was so much antigen present that we could detect it by a simple technique like agar-gel diffusion. These little particles became crucial because they could then be collected, isolated from the virions, and shown these in the upper left-hand corner. These little circles became the basis for the first hepatitis B vaccine. It was just purified antigen derived from plasma. That was the first vaccine that was developed by Maurice Hilleman at the Merck company. This vaccine, as you know, is highly efficacious, and if it could be disseminated throughout the world, as it's happening slowly, could almost totally prevent new cases of hepatitis B. But also, with that antigen, one now had a test. By now it's called hepatitis B surface antigen. And the next important thing was shown the association between this antigen and hepatocellular carcinoma. And we now know this is one of the leading causes of hepatocellular carcinoma in the world. So a lot came out of this very serendipitous finding. Now, again, as a government worker, I just will take some breaks during my talk to change the pace. But as a government worker, we are often accused of being lazy and on the government dole. But I just wanted you to know, as my audience here, that I myself always give 100% at work. It's just that it has a peculiar distribution. Now today is what, Thursday? This is not my best day of the week. I want to switch gears now from B to, I then went on to do these studies, prospective studies of post-transfusion hepatitis. And these were in open heart surgery patients, and the two keys to this study were that we collected the donor samples and saved them, and we got very frequent sampling on the patients after they had blood transfusion, every 1 to 2 weeks for 12 weeks, and then monthly for 6 months. It was these stored samples that became so valuable because we could go back as new tests emerged, we could go back and reanalyze these. So what we first found in these prospective studies, that the rate of hepatitis, when you didn't look for clinical cases, which were rare, but when you looked for ALT, transaminase elevations, they were very common. And in fact, over 30% of our open heart surgery patients were developing post-transfusion hepatitis. They were getting a lot of blood, as shown there, 17 units per case. And we're also getting a lot of blood from what we call paid or commercial blood donors. So in 1970, we introduced the first generation test for hepatitis B, but more importantly, we switched to an all-volunteer donor system. And that affected a huge, dramatic decrease, a 70% decrease in post-transfusion hepatitis rates from about 30% down to near 10%. Nothing we've ever done since that time was as important as cleaning up the blood supply and insisting that that donors not be paid, but that they come for altruistic reasons. That makes such a big difference. And this showed you that when a patient got at least 1 unit of commercial blood, there was a 51% chance of getting hepatitis, whereas they got only volunteer donor blood, it was only a 7% chance. In 1973, Abbott developed a third-generation test for hepatitis B, and we went back to these stored samples and found that most hepatitis was not really due to hepatitis B in the US. Only about a quarter was hepatitis B. So we had uncovered a non-B hepatitis, if you will, of unknown etiology. We thought it might be due to hepatitis A. That was the only other known virus, but it didn't fit with A epidemiologically. And then in 1975, Feinstone and Kapickian and Purcell, from your right to your left, at NIH, they were our co-workers, but it had nothing to do with this, but they discovered the hepatitis A virus. So we immediately tested our non-B cases for hepatitis A, and not a single non-B case was due to hepatitis A virus. It was then that we brilliantly deduced that if these cases were not A and were not B, that we would call them non-A, non-B. We thought this term would just last for a short term until we actually found the virus and proved it, but unfortunately we did not for a long, long time. But we now had non-A, non-B hepatitis. And the next big step was to take samples from non-A, non-B cases and prove that it was a virus. And we did that by transmission to chimpanzees using viral-like fractions. And all the chimps that we infected, we injected, developed transaminase elevations suggestive of hepatitis. So we proved transmissibility, but also not only could we show this from patients who had acute or chronic hepatitis, but we could show it from asymptomatic blood donors, people who were perfectly healthy, came to donate blood, and yet they could transmit hepatitis to the chimpanzee. The next event that happened was this patient, Mr. H, who's become famous. He was the first non-A, non-B strain. One day while he liked to blaze trails, and he was climbing a mountain, I think this may have been in Brazil. Anyway, he had a cardiac arrest while climbing. Would have died on the mountain, except that his wife was there, and she gave him CPR, saved his life, and he eventually made it to NIH, where he was found to have triple coronary vessel disease and went to surgery. As shown here on your left and in the blue are the ALT elevations. So 6 weeks after surgery, he developed transaminase elevations that went up to over 2,000. He was jaundiced at that time. And I was fortunate that on the ascending limb of his ALT elevation at point A, we collected a plasmapheresis unit. So we had a lot of plasma. And later on, after the virus was discovered as hepatitis C, we could go back and show at that point he had 3 times 10 to the 7 copies of the virus per ml. That material was then put into a chimp and titered in the chimp. And importantly, we now had a known infectious inoculum, and we had the chimp model. So although we hadn't seen a virus and we didn't really have a test at that point, we could take the virus-containing material and manipulate it, and then put it into the chimp as a model system to see if hepatitis developed. So first with Steve Feinstone and Bob Purcell, we took this material and did a chloroform extraction. And when you extracted with chloroform and then put it into a chimpanzee on the bottom, nothing happened. There was no hepatitis. But if you did a sham extraction, the chimp developed hepatitis. So this told us that the virus had a central lipid in this membrane. It was lipid enveloped, which is a very important distinguishing point. And then we did filtration studies, again with Dr. Purcell's laboratory, and we could push things through different size filters and then test the filtrate in the chimp model. And that led us to deduce that the non-A, non-B agent was both lipid encapsulated and quite small, somewhere between 30 and 60 nanometers in size. And this narrowed the viral possibilities down to either it being a totally new viral class, which I thought it might be, or that it would be a small RNA virus, the so-called alpha or flaviviruses, or that it could be a hepatitis B-like virus or a delta-like virus, but we had a lot of evidence that it wasn't B and it wasn't delta. And therefore, it came down to probably being a small RNA virus, and as it turned out, it was a flavivirus. So again, all this was known before anything was seen or tested for. Now, we then had the issue of whether this was a clinically significant disease, because a lot of people believe non-A, non-B was just a transaminitis. But when we did liver biopsies on 39 patients, we found that 10% already had cirrhosis, and another 13% had severe chronic active hepatitis, as it was called then, that would go on to cirrhosis. And then when we did repeat liver biopsies on some of these patients, we found that most of them were stable or even improved on the biopsy, maybe by sampling error, but 25% progressed over the years after their initial biopsy, leaving us with 8 patients out of the 39, or 20%, who developed cirrhosis. That 20% figure has held up pretty well over the years as being the usual rate of cirrhosis in hepatitis C. And importantly, among those with cirrhosis, 3 of our patients died of liver failure, and 3 more had severe liver disease and died of something else with their liver disease. I got tired then of working on this for a while, so I went into the philosophy. I tried to address some philosophical questions. For instance, if a man speaks in a forest and a woman is not there to hear him, is he still wrong? Now we know the answer to that one. But then I addressed the question of, Do infants have as much fun in infancy as adults do in adultery? Again, we're not sure though. So getting back to this story, which kept evolving over the years, you can see our hepatitis rates gradually went down as we did different interventions, ALT testing of donors, AIDS testing, and finally in 1988-87 we introduced anti-hepatitis B core testing as a surrogate marker for non-A and non-B. And our rates went down to about 4.1%. And through all this time, we had been trying to find the virus and tried everything we could, including early molecular biology. We did some subtractive cloning, but were unable to find the virus. And it was at that point, in my frustration in 1989, that I wrote a poem called I Can't See the Forest for the HBAGs. And it went, I think that I shall never see this virus called non-A, non-B, a virus I cannot deliver, and yet I know it's in the liver. A virus that we often blame, but which exists alone by name. No antigen or DNA, no little test to mark its way. A virus which in our confusion exists alone just by exclusion. But is it real or an illusion? Oh, great liver in the sky, show us where and tell us why. Give us thoughts that will inspire us. If we don't publish soon, they're going to fire us. I think it was that poem that was the stimulus for the Chiron Corporation to clone the hepatitis C virus. I'm not going to go into this cloning experiment, but it was quite clever. And it was Michael Houghton pelleted serum known to be infectious in a chimp, extracted the RNA, split it into, reverse transcribed it to complementary DNA, then importantly inserted into a phage GT expression vector so that any nucleic acid, any gene expression would then get into E. coli. They then lysed the E. coli, collected the expressed proteins on filter paper, and screened them with what they presumed were samples that might have antibody to the non-A, non-B agent. They went through, I'm told, 6 million clones before they found a single clone that was reactive. So this is great perseverance. This may seem easy in today's world of molecular biology, but at that time, in 1988, 89, this was really groundbreaking experiments. I think Nobel Prize worthy, but Houghton has not yet gotten the Nobel Prize. This is a picture of Michael Houghton on your right, receiving the Alaska Award, which I was very privileged to share with him. And on your left is Dan Bradley from the CDC, who was also very important in this cloning experiment. When Chiron discovered this clone and then developed an assay for antibody to the expressed antigen, they came to me because I had a panel, which was a small panel of well-pedigreed samples that had debunked. There had been many claims of a non-A, non-B agent before that, but nobody was able to break this panel because it had duplicate samples in random places in the panel and a lot of negative controls. But the Chiron Corporation, under code, found the 3 chronic non-A, non-B patients in 6 different samples, randomly spread. They found it in 2 implicated donors, again, in 4 samples, randomly spread throughout the panel. They missed the 2 acute non-A, non-B cases, but that's because they hadn't yet developed antibody. But subsequent follow-up of these 2 patients were also positive. And importantly, none of the 7 negative controls in 14 different samples were detected. And so they had a perfectly clean experiment. We then looked, using this antibody assay, 15 of our best non-A, non-B cases, every one of them seroconverted for anti-HCV. They were negative before transfusion, positive after transfusion. So we then knew that non-A, non-B and hepatitis C were synonymous. And then we looked at the donors to these cases of 25 different non-A, non-B cases. We found a positive donor, first in 80%, but then with a second generation assay in 88%. So we predicted that introducing this anti-HCV assay would prevent about 90% of post-transfusion hepatitis. Indeed, that's what occurred. So we introduced the first generation test in 1990. The rates went down to 1.1%. The second generation test came out in 1992. And by 1997, we had reached virtual zero incidence of post-transfusion hepatitis. Now, it isn't really zero. It's all we could measure in these kind of studies. But the risk now is about 1 in 2 million. So we started at 1 in 3 and wound up with 1 in 2 million. Quite remarkable. This is that same slide, just showing a downward arrow. I show that because this not only represents viral hepatitis, but this represents my life. And you can see that both viral hepatitis, post-transfusion, and my life are on this very sharp decline. And I'm just happy that I'm still standing here able to tell you this story. We can project, based on the instances we had of post-transfusion hepatitis, of 10% in the 70s and 6% in the 80s, that if we projected this to the entire US population, that there were probably almost 5 million cases of post-transfusion hepatitis, non-A, non-B, caused in the 2 decades from the 70s to the 90s. And this would have resulted potentially in 20% cases of cirrhosis, so there could have been as many as 768,000 cases of cirrhosis induced by transfusion. It wasn't that high because many of these patients died from their underlying diseases before they would get cirrhosis, but the potential was there. In contrast, when testing was introduced in 1990, if it had not been introduced at the rate of 4%, which is where we began in the 90s, there would have been another 1.2 million cases of hepatitis, or 192,000 cases of potential cirrhosis. So this is what was prevented in the first decade after the testing was introduced. Now, again, I wanted to move off from strict science, so I did another study. Everything has to be evidence-based these days. So I did an evidence-based study of the chances of a man winning an argument at different times within his relationship. And you can see that while you're dating, you have about a 50% chance of winning. But once you're engaged, it goes down to 25. And once you're married, you have no chance at all of winning this argument. This is evidence. I can attest to it. Now, looking at the world burden of viruses, there are 350 million cases of hepatitis B in the world, 170 million cases of hepatitis C. About 5 million of those are in the US, so most of them are outside. And the reason there are so many cases of hepatitis C is because 75 to 85% of people who get the infection remain persistently infected. So for a moment, I want to look at persistence. So there are several reasons why one is persistently infected, but this is the very important one. And that is that the virus exists as this viral quasi-species, a family of viruses. Nobody has just a hepatitis C virus. You always have a family of viruses, of very closely related but potentially immunologically distinct agents. So with Patricia Farsi, we looked at 105 clones of hepatitis C from this single patient I showed you, Mr. H. And he had 57% of his clones were identical, but at the same time, he had 19 other clones that were already present in his serum. And if we'd done 1,000 clones, we would have found even more. The point is that even if he had developed a good antibody response or T-cell response to the major predominant agent, any one of these other agents could have immediately emerged and taken over to keep the virus persistent. I've done this little schematic, which is very simplistic. I apologize to the immunologists in the audience. but I think it gives you a visual picture of what happens. The first thing in hepatitis C is that the virus replicates very rapidly. It doubles every 13 to 17 hours. So within the first week of infection, one is already up to 10 to the 5 to 10 to the 8 copies per ml. It's at the maximum, you reach maximum level within 1 to 2 weeks. This is before the immune system ever kicks in. So by the time the T cells might respond to the virus, there's already a huge viral load that overwhelms the T cell response and causes an anergy, a very specific exhaustion of the hepatitis C reactive T cells. Then you have this evolving quasi-species. This quasi-species is now producing a lot of viral proteins, a huge amount of viral proteins, particularly the non-structural proteins. And these proteins are inhibitory, first to the innate immune system, and then also to the B and T cells, particularly the T cells. So normally T cells would produce perforins and fast ligands and interferon gamma, which would help to contain the virus, and the B cells would produce the antibody. So in a normal situation, these T cells and B cell antibodies would work on a quasi-species, narrow it down, and eventually 15 to 25% of patients can spontaneously clear the virus. But what usually happens is that these T cells are blunted, and you don't get these interferon gamma responses. And the B cells, the antibody, instead of getting rid of the virus, actually drives further variation of the virus. So the quasi-species continues to expand, and then you've lost the ball game and you're into persistent infection. Now, clinically, we've seen 3 classic models of hepatitis C. Most patients have this long, stable course where they become infected. The HCV RNA is shown in the red. They become infected early. They can develop a hepatitis. It usually gets mostly contained, although not eradicated. They develop antibody, and they go on to this long, indolent course. About 20 to 30%, we now know, go on to cirrhosis over the course of 15 to 40 to even 50 or 60 years. And a small number have this very rapidly progressive course where they may die or develop cirrhosis in 5 to 10 years. We're studying now, I'm not going to have time to go into what is the difference between these slow progressors and the rapid progressors. And there are cytokine differences that may account for it, and chemokine differences. But when you follow patients, these are our asymptomatic blood donors who we followed for a long time. This is analysis after 22 years, but it's gone now over 30 years. But what we find is that a very small number, if you look just at the bottom panel of fibrosis, most patients have no fibrosis or very mild fibrosis. 12% had severe fibrosis, and 1.6% had cirrhosis. So over the course of the first 25 years of infection, less than 15% of people have a bad outcome. That was shown also in women who received contaminated lots of Rh immune globulin. This was in Germany, but it also happened in Ireland, where the patients were followed very carefully and had liver biopsies. And after 25 years, among these healthy women who then got infected at the time of pregnancy, after 25 years, 9% had bridging fibrosis that might go on to cirrhosis, and 2% had cirrhosis, so again, under 15%. But shown on the right, there was a trend towards worsening disease over time. So what we now know is that over the first 20 years, 15 to 20% of people with hepatitis C might have severe outcomes. It's possible that after that, scenarios 2 or 3, that everybody could have bad disease, but it would take 40 to 60 years to develop. But there's already evidence against that. Everybody is not going to get sick. It's possible that if you haven't developed a bad disease by 20 years, you may never develop it, scenario 4. But what's probable is scenario 1, where the trend will continue, and now out to 40 years, where some patients have been followed 40 years since their exposure, the rates of severe outcomes are going up to 30%, and it may well continue on that trajectory, so that after 50 years, it'll be 40%, after 60 years, it'll be 50%. And we do worry that with age, with the immunodeficiency of aging, that it may get worse after people get to be in their 70s or 80s, which is also when hepatocellular carcinoma tends to develop. Now, there are confounders that make hepatitis C worse. One is alcohol. And this is a nice study by Wiley that shows the effect of having HCV alone in red versus HCV plus alcohol. And this is quite a bit of alcohol. We usually indicate excess alcohol is drinking more than the investigators. But in any event, if you have both, you can see that the risk of cirrhosis about doubles. So people have excessive alcohol intake. This is more than 40 grams a day in men, 60 grams a day in men, about 6 drinks. The risk doubles. Now, I had 2 patients who I suspected of drinking. They were doing badly, but they denied that. They said they only had 1 drink per day, which was the allowable limit. So I mistrusted their history. So one day after clinic, I went out and I followed them out after clinic surreptitiously, and I found in fact, they were telling the truth. They did have only 1 drink per day, but this was it. The other big confounder now is NASH, or steatohepatitis with the metabolic syndrome. This nice study by Bedosa shows that if you have chronic hepatitis C alone, after 22 years, 16% have severe fibrosis. But if you have steatosis plus chronic hepatitis C, it doubles to 32%. And if you have full-blown NASH, the full-blown metabolic syndrome, it goes up to 54% of a bad outcome. So obesity, especially in America, is a major problem. Just to show you how bad things are in America and obesity, this is a picture of the Statue of David after spending 6 months in America. And you can see what happens in our country. Now, our big concern now is hepatocellular carcinoma. The rates of hepatocellular carcinoma are going up. They tripled from the late 1970s to the late 1990s. It's because people are having their infection for longer times. They're having it now for 40, 50, 60 years, and this is when the carcinoma tends to evolve. And shown on the right, you can see it's all due to hepatitis C. All the increase is C, not B, or not other variables. It was projected in 2009 that if something didn't change, that over the next 20 years, that there would be a 4-fold increase in decompensated cirrhosis, in hepatocellular carcinoma, in the need for liver transplants. And this projection was coming true, as I just showed you. The rates were going up for all these events. But fortunately, something did change. What changed was the treatments. We've now had this dramatic increase in treatment efficacy, starting with early interferon treatments. We had 6 to 16%. Then ribavirin was added on. Then pegylated interferon was added on. But in 2011 came these direct-acting antivirals, these HCV-specific designer drugs, first for the protease, but then for the polymerase and the NS5A replication complex. These have had dramatic impact. Efficacy is now over 90%. I'll show you the most recent study. There was an ASLD this year, and published this year, that among 624 patients, of whom 19% already had cirrhosis and 32% had failed prior treatments, that 99% had a sustained virologic response that is tantamount to a cure. If you have so-called SVR, you are basically cured. And in a companion study, this was for genotype 1, but a companion study showed that even for genotype 3, which is the most difficult to treat, that there was greater than 95% cure rates. This is unbelievable. I could not have imagined this. This is an oral pill taken for 12 weeks with almost no side effects. This was to indicate something, but I don't remember what. But with cure rates now approaching 100%, I believe that from this time forward, once you have identified HCV infection, that no one should develop cirrhosis if they don't already have it, and no one should die of hepatitis C unless they already have advanced disease. We should be treating all these people to cure. But who's going to take responsibility for this? We cannot access the drugs. Even at NIH, I cannot get the drugs because of the cost of the drugs. This is the economics of hepatitis C. In the US, we have 3.2 million people infected. In the world, 150 million people infected. A 12-week regimen of this curative therapy in the US costs $50,000 to $84,000, or $600 to $1,000 a pill. So these direct-acting antivirals have been shown to be cost-effective in the long run. They prevent cirrhosis, they prevent transplantation, they really save money. But the upfront costs are prohibitively high, being estimated at $200 billion to cure the US population alone. And now there's another 150 million people in the world. So the resulting strategy in the US has been to treat those with the most severe fibrosis first. But this adds cost. This adds cost and complexity by requiring a biopsy or a FibroScan, and it leaves most patients untreated because most patients have relatively mild disease at this time. I think there's need for governments, for pharmaceutical companies, and for insurance companies to strike an equitable balance such that infected patients do not become the victims of these usurious profits that are being made right now. Somebody's got to take charge of this. And this is affecting, it's probably the worst in the US, but it's affecting Europe, it's affecting the rest of the world. Fortunately, the companies have made arrangements, such as in Egypt, to bring prices down. But it's a real problem. Despite the problem, we've made remarkable advances in the last 5 decades of hepatitis. Everything happened not in 2,000 years, but in the last 50 years. So we've identified hepatitis B, hepatitis A, hepatitis delta, hepatitis E, and non-A, non-B HCV. We've established a strong link between HBV, HDV, HCV, and hepatocellular carcinoma. We developed vaccines for B, A, and E. We've had the virtual eradication of post-transfusion hepatitis. We've had successful transplantation for hepatocellular carcinoma and for end-stage liver disease. We have highly effective long-term suppression of hepatitis B with oral nucleoside and nucleotide inhibitors. We have greater than 95% cure rates in chronic hepatitis C, as I just told you, using oral, safe, direct-acting antivirals. So is it possible, or even likely, as I believe, that hepatitis B and C could be eradicated over the next 3 to 5 decades? I think it's possible. I don't think, though, that I will be doing it, or maybe even be here to see it. So, because with that in mind, I've developed a new curve of the effects of aging on my philosophical viewpoint. And you can see here where age is on the abscissa, and on the ordinate is give a damn. And you can see this is me. So I'm out here. I will not be here for the end of the story, but I hope you young people in the audience will make this dream come true, that we can really eradicate with vaccines, with recognition of cases, identification of cases, with treatments that are affordable for everybody, that we could really eradicate B and C. So there's great hope, and I hope you people will carry this on. Thank you very much.